Okay, it's 8 o'clock my time, 1 o'clock Zagreb time. So welcome today for the session on lightweight design. I'm happy to see that we have a good number of papers, and as you know now, the process is that we will first hear all in one shot the prepared videos, and then we will open it up for discussion. We can use the chat to pose some questions, and we will all try to monitor the chat so that we don't leave any questions unanswered. So I should also mention, just on a personal note, that we had a thematic collection in the Design Science Journal all of last year and a half on lightweight design. And so those of you who are not aware of it, you may want to go to the Design Science Journal's website and look for the thematic collection, which is like a special collection of papers on this topic. So with this, Robert, will you please start the presentations? Thank you all for attending.
Hello, my name is Patrick Hommel, and I'm happy to present you our contribution about deficits in the application of aluminum foam sandwich. A great potential for lightweight design lies in the use of sandwich materials, and one innovative material is aluminum foam sandwich, which consists of aluminum alloys in the face sheet and also in the foam core. This material has many advantages. For example, a low density at a high bending stiffness and also good energy absorption properties. Although AFS has many advantages and various possible fields of application, the material is still not used that often in industry. But the reasons for the low number of applications are not sufficiently known yet. To identify the obstacles to the use and to understand the needs of the customers, we conducted a survey in which 65 people participated. Following research questions should be answered by the survey. So first, what are the obstacles to the use? And second, is support necessary for designing with aluminum foam sandwich? First, the participants were asked if they knew of AFS before the survey, and in total 89% said that they knew of the material, although some of them don't know any characteristics. And additional questions showed that only half of all respondents included AFS in their material selection at all. And then only about a quarter of all respondents used AFS in current or previous projects. So at this point, the most important question remains, why do most of the participants do not use the material or even consider it in the material selection? Here on this slide, you can see the most given answers to the question concerning the obstacles. More than half of all respondents answered with the high cost of the material. And then the lack of design knowledge for the material, as well as the lack of reference applications, were further answers. Here you can already see that the participants are missing some special design knowledge, and most of them didn't know where the material could be used effectively. In the last part of the survey, we asked the participants if engineers needed help when designing with AFS. And half of all respondents answered that they need support, while only about a quarter answered that they didn't need support, and the rest were undecided. Especially when you think of the fact that some of the present users were also asked, I would say that the 49% who need support show you that even the people who are already familiar with AFS still need some more help. And in another question, the user were asked which information was missing during the design, and how the designing with AFS could be simplified. And the most given answers were the design catalogs or design guidelines, and other answers were an overview of processing options or an overview of the fields of applications. The last two questions I will present you now were about whether a document or a platform with the material notes could be a support for designing with AFS, and if the participants would use such a document or a method. And the clear answer was that 82% think that this will be a helpful support, and 71% would use such a support. So in conclusion, the survey identified the obstacles to the use of AFS. And while the price will decrease with increasing use of the material, the lack of design knowledge and the missing reference applications suggest the need for more research. I think AFS is a great material, but we need a support method in order to improve and increase the application. And there are already many ideas for support, like a design guideline with necessary design knowledge. And in the next steps, the content and the best form of this support has to be elaborated. So thank you for your attention, and I'm looking forward to the discussion.
Welcome, everybody. I'm glad that you have joined the presentation online. My name is Sven Revfi, and I'm from the IPIC Institute of Product Engineering at the Karlsruhe Institute of Technology, KIT. Today, I want to speak about the design readiness of multi-material concepts. Let us start with the motivation. Products are developed in generations. Therefore, every product development is based on a reference system, shown here for the development of a new strut tower. This use case originates from a real development project where a lightweight design strut tower had been developed. At some point in the development process, one is faced with the challenge of having to decide on one of the many concept ideas developed. This is also the case here, visualized by 3 concept ideas as examples. Now, in order to make a decision with which concept you want to follow, you have to ask yourself different questions. What is the time to market? What do the available resources look like? What about the concept maturity? For lightweight products, where multi-material design has proven to be the most promising approach in recent years, the question of the manufacturing and joining technologies required to implement the concept is particularly relevant. Therefore, this publication deals with the topic of how to generate an objective assessment of maturity levels in multi-material design concepts. Let us first take a look at the state of research. For the maturity assessment of technologies in development, the technology readiness level presented by NASA describes different maturities on the basis of verbalized criteria and by using an ordinal number scale from 1 to 9. The TRL focuses on the assessment of an overall system and does therefore not consider maturities of individual subsystems. The effort required to raise the TRL can vary greatly depending on the current level, since different activities must be performed to achieve different TRLs. Consequently, the TRL does not represent the amount of work required to reach the current TRL and does not provide an estimation for the amount of work required to reach serious maturity. To assess different subsystems and their interactions in respective to an overall system, the system readiness level is used. Here, the subsystems are assessed with a TRL as presented. The interfaces connecting the subsystems are assessed with an IRL, again using an ordinal number scale based on verbalized criteria. By using mathematical operators, the whole system readiness is calculated based on the ordinal numerical values for TRL and IRL, although mathematical operations with ordinal values provide invalid results. From the presented state of research, the following research gap can therefore be identified for the evaluation of MMD concepts. There is no objective and integrative manufacturing and joining technology assessment, including temporal technology development. For this reason, we have developed the design readiness level for multi-material design concept. This includes the the prediction or extrapolation of future technology development based on the development in the past, the TRL as the predicted manufacturing technology development, the IRL as the predicted joining technology development, and additionally allows the calculation of a design readiness level, DRL, by cardinalizing the TRL and IRL values. The design readiness level is now illustrated by an example development of multi-material design concepts for a gearbox housing. The already existing reference system is manufactured with steel casting. All upcoming values are exemplary and should reflect the assessment of TRL and IRL of a fictitious company. For concept 1, components manufactured by steel casting and an aluminum casting are to be used. For components 1, 2, and 5, TRL 9 represents that the components have already been used in the reference system and are therefore tested for use. For components 3 and 4, aluminum casting has been sufficiently validated as a manufacturing technology for this application, but has not yet been validated for use. This also applies to the chosen joining technologies between components 1 and 4, representing an IRL of 7. For the joining technology used for components 3 and 4, tests have already been carried out in addition to the validation, so that it is assessed with an IRL of 8. From the consideration of the temporal developments of the individual manufacturing and joining technologies, the prognosis has shown that it will still take about 6 months to reach series maturity for the manufacturing technology of aluminum casting. A current design readiness level of 0.89 was calculated for the overall concept, where a DRL of 1 represents full series maturity. If this is compared with a second concept using fiber reinforced polymer injection molding for the components 3 and 4, a manufacturing technology in whose application the fictitious company has not gathered as much experience as with aluminum casting, the implementation of this concept will take more time, which is represented by the lower DRL. Nevertheless, a bigger weight reduction potential exists. According to this, the DRL offers an added value for product development by considering temporal developments of individual manufacturing and joining technologies in respective of an overall system assessment. This brings me to the end of my short presentation. I would like to thank the DFG for its support, and now I look forward to an interesting discussion.
Hello, my name is Eike Uttich. I work at the Chair for Product Development at Ruhr University Bochum as a researcher in biomimetics. Biomimetics is the transfer of solutions from nature to technology. My special research interest lays on the human locomotive system, in particular the arm and the leg. One principle that contributes to the lightweight design of the arm and the leg is the tension calling principle. It names the effect of muscles and their neuromuscular control on the bone, which is a reduction of bending and load adaptivity. In our paper, of which I'm presenting the results today, we investigated the effect of a principle if used for torsion in addition to bending for a minimal example. The biomimetic approach we use is called bottom-up. In this approach, we start with a solution in nature and search for technical applications. Systems in nature are complex, so the number of aspects transferred from nature to technology can vary depending on the technical application or problem. In the middle of the slide, 2 abstract systems are displayed which are both inspired by the human arm. That is, both systems use a biomimetic motion planning and topology optimization, just like in nature. They are different in the actuation concept. In the upper system, joint engines are used to actuate the arm. The lower system uses redundant pulleys as a bio-inspired actuation, which we call the tension calling principle. In comparison to the upper system, 30% mass of the segments can be saved in the lower system. The next step is to find technical applications for the yet abstract technical solution. These applications have specific boundary conditions. The excavator arm shown on the right experiences high torsion loads besides the bending loads, for which the effect of the principle was already shown. Therefore, we wanted to investigate to which extent and cost torsion can be reduced by the principle. For the investigation, we used a minimal example. That is a cylindrical beam with a revolute joint and loads at the end of a beam held in the displayed static position by actuation forces. To include form optimization, we use a simplified approach that adapts the diameter of beam segments to the maximum Vermeer stresses they experience. We investigated 5 actuation cases. Case 1 is an actuation force located on the beam axis at the end of a beam. Case 2 and 3 are one force located either on the left or the right side of a beam. The force acts on the lever arm, which transfers the force to the beam. The lever arm allows to create torsion. Actuation cases 4 and 5 include 2 forces, one on each end of the lever arm. In case 4, both forces point into the same direction, while in case 5, one force direction has a negative and the other force direction has a positive Y component. There are 2 loads that are attached to the end of a beam. One load results in bending along the axis of a beam, and the other is a torque that leads to a constant torsion on the beam. We combined form optimization and force calculation in an optimization that targets a minimal structure volume. We also varied the angle of a force to the beam axis in the XY plane. The results displayed on this slide show the relative volume of a beam over the angle. Relative volume is the volume of a beam after the optimization compared to the volume of a beam actuated by a joint engine, so a moment, a torque in the revolute joint. We found that actuation cases 4 and 5 lead to the lowest relative volume for all load cases. These are the only load cases which can react to both bending and torsion. As expected, we found that for small angles between force and beam axis in XY plane, the joint engine is an advantage. The difference between actuation case 1, which only compensates bending, to actuation cases 4 and 5 can be explained as these actuation cases introduce an additional bending moment, which is constant over the beam axis due to the position of the forces. In general, we found that torsion can be compensated by the actuation principle, but it comes with a cost. Besides the additional actuators and their weight in the system, they introduce additional bending moments in the system. Depending on the material used, these moments require compensation for the principle to be beneficial for the overall system. From the perspective of the application, several questions cannot be answered with the approach, including: are the actuators quick enough to compensate eventually occurring torques? What is necessary to sense the torque? How do the boundary conditions restrict the positions of the actuators and their effect on the structure? These questions and many more must be considered in the technical application of the principle, and I'm looking forward to the discussion. Thank you for listening.
Welcome to the presentation of my submission, Factors Influencing the Decision of Conventional Hybrid Lightweight Design Strategies and Their Effect on the Design Process. My name is Pascal Schmitt, and I'm from the Chairs of Product Development and Lightweight Design at the University of Rostock. Product requirements can be contradictory. One famous example, the automotive industry, where customer needs tend to increase the weight. One way to solve this contradiction is to use lightweight design strategies. However, as conventional lightweight design is reaching its limit, new technologies and approaches are explored to meet these challenges. This paper forwards the additive manufacturing and the approach of a hybrid lightweight design. I will also take on the general strategies influences on the design process and properties. Therefore, selection criteria are defined. The common approaches of lightweight design can be separated in the following 5 strategies. Structural lightweight design, aiming at the maximal exploitation of the permission stresses in the structures. Composite lightweight design, combining materials to utilize the advantages of their different material properties. Conditional lightweight design, aiming at minimizing safety factors. Material lightweight design with the goal of weight reduction by substituting material with alternatives with better specific properties. And the conceptual lightweight design, where the entire system is optimized with regard to lightweight design goals. These strategies can be allocated in the design process, as you can see in this figure. This figure shows the selection criteria and their interdependencies with each other. These need to be considered when selecting a suitable lightweight design strategy. This way, it can be determined whenever dependencies are rather positive or negative, and trade-offs can be identified. A special focus is on the criteria with the direct influence on the product architecture. For example, customization, high functional integration, or high adaptability. One trade-off can be named in the negative dependency between higher functional integration and a higher level of customization. Another one between the customization and a low weight. A comparison of the selection criteria and lightweight design strategies allows a better understanding of their effectiveness. The complexity of a three-dimensional comparison can vary. Some are more obvious, like the reduced weight, while some are more complex due to the different perspectives of customers and developers, like costs. The strategy of composite lightweight design should be given as an example, as although it can be found a wide field of application, it has a number of negative effects in different criteria. Several studies have shown that AM is a promising approach to overcome the named trade-offs. A methodical support of positioning AM in the design process with regard to lightweight design is not yet sufficient available for designers. The allocation of AM could be seen in the following areas. Thank you for your attention.
Hello, ladies and gentlemen. I welcome you to my presentation entitled An Approach for the Multi-Criteria Derivation of Lightweight Potential. And when you want to derive lightweight potential, you usually ask the question, where should lightweight design be applied? And the phrasing where should usually asks for the motivations for lightweight design. So to apply, why do you want to apply lightweight design in the first place? And the answers are numerous. You want to reduce weight to improve performance, for example, or you want to reduce weight to reduce the energy consumption during use, and so on and so on. And we ask ourselves the question, how can lightweight potential be derived against this multi-motivational background? And in the paper, we showcased a processing machine consisting out of a frame, which you can see here in gray, and a motion unit performing a two-axis motion indicated by the red arrows right here. And the motion unit itself comprises a vertical card in blue, a horizontal card in green, and an operating fork in yellow. And this processing machine, the motivations for performing lightweight design were threefold. First of all, reduce energy consumption during use, measurable in watt, improving performance, and lower the center of gravity. And on the right-hand side here in this table, you see the different units of these motivations, like the criteria of these motivations, which are measurable in watt, meters per square seconds, and meters for lowering the center of gravity. And the question now is, how can you combine all these motivations in one single measure to actually compare the lightweight potential of the different assemblies? To show you on the example, reduce energy consumption, so the first motivation, so to speak, the first criteria measurable in watt. And the question here is, how does lightweight design influence the energy consumption of all the three assemblies? And this is a thing you can actually measure. And how do you do that? You apply the same amount of lightweight design, so of mass reduction on all three assemblies. And when you do that, you measure, or you calculate in this case, how much the energy consumption is reduced. And then you can write down here at the x-axis the different energy reductions for each single assembly. And then you have to do something to compare this motivation to all the other motivations. And how do you do this? You work with a dimensionless abstraction level, here called the degree of fulfillment. And the degree of fulfillment is a range ranging from 0 to 6 points, where 6 points is the best scenario. In this case, we said saving 10 kilowatt in energy is equal to 6 points. And then you can assign the different assemblies to an individual degree of fulfillment. And this you can do for every single motivation. Here you see the reduction energy consumption during use, which you have just seen in the table on the previous slide. When you do it for all the other motivations, you find the other dimensionless numbers, which are calculated and measured individually for every single motivation with a single and an individual measure. And then you can weight the different motivations against each other, and then finally calculate the net benefit, which is actually the lightweight design potential you see here in the last row. When you look at the lightweight potential, you see that the vertical card especially, and the horizontal card as well, display the highest lightweight potential comparing to the operating fork. And when you then look at the old design, which you can see on the left-hand side, and have these different lightweight potentials in mind, we derived and conceptualized a new concept. And you see that especially the horizontal card and even more the vertical card are designed much smaller with some topology optimization at the horizontal card. So the two assemblies with the highest lightweight potential were then reduced in mass for the highest amount, comparing to the operating fork, which stayed mostly the same and also following the lightweight potential of the operating fork, which was comparably to the other assemblies quite small. So thank you very much for your attention, and don't hesitate to ask any questions. Thank you.
Well, thank you everyone for the presentations. I would like to invite everyone to mention some points in the chat. I would like also to, if someone wants to speak, you can ask us through the moderation panel, and I will let you speak. Right now, as you know, the process is the individuals that you actually see their names underneath the screen have the ability to talk. Everybody else will ask, and either myself or our assistant Robert will let you come in. And if we exceed the number of 9 speakers, then we will have to kick somebody out. All right, so that's the rules of the game. While you're thinking about it, I was going to start with some questions, if I may. Felix, I have a sort of general question. In your example, you basically have a 3-dimensional Pareto problem, right? You have 3 objectives that are competing.
Exactly.
And so I would think of it as a standard, standard multi-criterion optimization problem. And I assume that you're looking at it, you do a decomposition of the system into subsystems, and then you look at its subsystem. And what I don't quite, I didn't catch is how this index that you call degree of fulfillment, how does it relate to the Pareto surface? You know, you have a 3-dimensional Pareto surface. If you think of it as a standard optimization problem.
Yes, I understand your question.
Is that another, is that a combination? Yeah.
When you look at the
if I may just add one more thought. I was going to say that usually, if we want to get a single point, we think of some kind of scalarization, right? You can put weights on the three objectives of some other higher level utility function that combines the objectives internally. And it seems like this degree of fulfillment sort of does this. So I'm just curious to see what your thoughts are.
Yeah, thank you very much for the question. I think the point is the basis of this analysis, how I designed it, lies at the basic structure of cost-benefit analysis. And what you do in cost-benefit analysis, you try to combine different criteria with different units. I hope this came through the presentation. When you now ask how do these different criteria interconnect with each other, then the most important thing when you're talking about the Pareto optimum of these three different criteria is then of special importance when the rising of one criteria decreases the performance of another criteria. And this actually will be the next step to include in this analysis, because now I only, before calculating the entire benefit value, I only check the criteria against each other, which criteria are interconnected. So when the criteria 1 changes, the criteria 2 is being influenced. And then the optimization has to take this into account. But the current state of the analysis is that I do not derive a Pareto front and optimize on this Pareto front. And I think I didn't answer your question completely, because your question was also like the degree of fulfillment. The degree of fulfillment is just in the dimensionless abstraction level, which makes the different criteria comparable to each other, but do not consider interconnections between the criteria, like criteria 1 influences criteria 2.
Okay, I understand. So it may be somewhat first phase in terms of understanding the trade-offs for finalizing the conceptual design. Like you showed in the example, your analysis motivated you to go and redesign the support of the cart.
The result of the analysis actually serves as a help for the designer, which assemblies should be prioritized when being reduced in weight. High lightweight potential means that you have to apply lightweight design first, and then second, and then third. Do you have any ideas how to implement? I mean, this is very far-reaching question, to implement these analysis you're talking about, like the Pareto analysis, finding the Pareto optimum between different criteria?
Well, I think that's what I was trying to understand. You have a good point that when you have three criteria that are not commensurable, right? They cannot be measured in the same units. You need to, in order to compare them, other than just drawing the curve and picking what point you like, is to form some type of, what we call a scalar substitute function, some type of utility function.
Yeah, I understand.
And then translate each of these criteria to a component of that utility measured in utils, right?
Yeah.
And oftentimes that is, it could be dollars or euros or something, right?
Yeah.
So
I'm thinking about when Ashby is using the Pareto optimal front to find out which material is working for the application at best, and then he draws a utility function for costs and drives it through the Pareto front and where the connection is.
Exactly. So that's basically
but that
a graphical approach, right?
Yeah. But correct me, that only works because every material, staying with the Ashby analogy, every material has a cost value, has a value which you can measure in cost.
Right.
Yeah. And this is a problem when you want to combine different criteria which are not interconnected with each other, because then it's not possibly in a direct manner to get clear about the influences of the criteria with each other. And I think that's
well. Again, you could translate each criterion into some type of cost, but anyway, I don't want to monopolize this. There is some, of course, George Fadel has a question. I'll get back to this, Felix, but let's see what Professor Fadel, he says, it is interesting to see the interest in lightweight design. What is causing this focus? Or he's more philosophical. Why everybody is talking about lightweight design? Is it the ability to design things differently? Is it cost issues? Or as some of you mentioned, some criteria that explain this, for example, the advent of additive manufacturing. So why would previous designers not focus on lightweight design? Maybe anyone would like to address that from the presenters?
I may comment your question. I think the thing is that there are new conditions, especially, or for example, during because of new technologies like additive manufacturing, and of course another point is the cost. And there are always two different perspectives. One is of the producing company, because it says that every intention of integrating lightweight design leads to additional cost first. But on the other hand, for example, for the customers, for the end users, it can often lead to a decrease in cost. So that is, I think, one special point. And yeah, this for the first. So maybe you can add something.
Yeah. Okay. Thank you, Pascal. I think Felix.
Yeah, if I may, I think there is no general answer to that question. It mainly depends on the branch, on the field you're working in to do lightweight design. For example, a lot of companies are not aware that lightweight design can actually be a tool to decrease costs. Mainly, then you look at your product from a structural point of view and try to find some inefficiencies in the design. When you try to remember the last slide I showed with the different cards, and maybe that also answer the question from Daria Vla. After performing the analysis only showed where to look first, and then second, and then third to apply lightweight design. What we did then was trying to actually reduce the mass. So we applied a lot of different lightweight strategies, like Pascal showed in his presentation. There are a lot of different lightweight design strategies, mainly 5, and with every single assembly, starting with the assembly with the highest lightweight potential, asking the question, where should we reduce lightweight design? The second question is, where can we reduce lightweight design? So where is it technically possible? So then we focused on to actually reduce the weight, applying all different lightweight design strategies. And coming back to the first question, if I may, next to like killing inefficiencies in the concept by doing lightweight design, thus reducing the costs. As I said before, it mainly depends on the firm and the company you're working with. When you work with companies who produce handheld products, then usually the motivation for lightweight design is that the customer who is holding the product during use has less mass at hand, and other companies are looking for different motivations because they want to reduce the CO2 footprint, for example, of their products, applying lightweight design to manage that.
Yeah.
Just to add a point here. Oh, sorry. Yep.
Yeah. Yeah,
Maybe
please go ahead, please.
Maybe just to add a point in a very general answer is for accelerated masses. Then you need lightweight design because then you can reduce the fuel consumption, for example, or the energy in the end, right? And you have side effects with transportation and recycling and so on and so on. So, but as you said, Felix, it is important to consider the branch you're in. For example, the automotive sector, they do a lot of lightweight design. Other sectors, not that much they could do, maybe.
Well, back to George's point, I think George, as the speakers already mentioned, you can see the drivers coming. For example, first area for lightweight design was aerospace because of the cost and the energy required to fly things, right? But then as energy became more and more expensive, and in addition to the use of fossil fuels, these were the key drivers. So we saw that more and more in automotive. So gradually, this became much more important because of energy needs. But then at the same time, we started looking for technologies that would allow us to do it, like additive manufacturing, like simulation-based sort of design. And so we had more and more techniques that allowed us to create lighter designs without repeated testing and prototyping. So it's sort of a natural evolution, I think. I think everybody tried to have lightweight designs within the context of the particular period of engineering, let's say in the last 100 years or so. Anyway, I wanted to ask a question that sort of relates to Pascal's and Felix's talk, because both of you discussed the issue of trade-offs. So, for example, Pascal showed what looked like a sort of standard QFD, right? The house of quality top of the correlation matrix as one way of exploring the trade-offs. And Felix also talked about sort of using a degree of fulfillment as a way of exploring the trade-offs. Do you see, what's the underlying problem in both of your cases? Is it making early decisions? Do you see a connection between sort of the ways that you both talked about these ideas of comparing alternatives?
I can start. Thanks for the question. I would say, the approach is a little bit different because I'm in the very beginning of my research. So I try to use this criteria to start from the ground and find what you said, the trade-offs, which we assumed, and we assumed to overcome some of these trade-offs by AM. But it's a literature review, and I think Felix's approach is more advanced. And in one special case, for me, it was important to get a general idea of the situation of the allocation of AM regarding to the lightweight design strategies. So I think that's one difference between our approaches.
Mm-hmm. Mm-hmm. Thank you.
Yeah, thank you, Pascal. I think you nailed the point. I found I just looked into your paper, and I found a lot of motivations for lightweight design within your criteria set. but also different criterias, more looking on, lightweight as I would say, as Klein puts it in his book, as an design philosophy taking place in all different parts of the entire product development. Like when you, for example, have criteria high safety and long lifetime, for example, these are two criteria which are usually not directly related to lightweight design, but by lightweight design being an entire designing philosophy, you definitely cross these kind of criteria when designing a product in a light manner.
Okay, thank you. Some other questions. I have some more questions for the speakers, but I wanted to see if others from the audience. I have a question for Sven. So I looked at this DRL matrix with a lot of values in it. And I was actually very impressed that you can do this type of analysis, such level of detail, and collect all these numbers. And so my thought was, so who generates these numbers? And, and the reason I will say, the reason I'm asking this question is that in some ways, these are subjective evaluations, right? The subjective numbers. And so if you have a reasonably complex design, you probably have more than one person contributing to the generation of these numbers. And now you have the problem of do two different people understand the numbers in the same subjective way? Otherwise, you will have discrepancies in the perception, right, of the judgment, and you start worrying about, okay, I have numbers, but do I really believe them?
That's why we extended the traditional technology readiness level or integration readiness level, because you're right that the original TRL is kind of very depending on a person's opinion. But what we did is we tried to include the factor time. So we tried to make the ordinal TRL numbers you mentioned. We tried to convert them to cardinal TRL number or cardinal coefficients, so that we have that factor of time. So how much time did it take us from TRL1 to TRL2? How much time did we need from TRL2 to TRL3? And out of this, we want to learn how much time we maybe need from TRL5 to TRL6 with an extrapolation in time. And so we have that factor time, which allows us to get cardinal numbers and not ordinal numbers, which are very depending on the person doing the assessment. Maybe for your first question. And the second question, how can you do this? It's a lot of work, you're right. But we applied this method in an industrial company, and they have they call it innovation backlog. And in this backlog, they collect all the numbers, all the technologies they look at, all the technologies they looked at in the past. And in this backlog, they noted how much time they did need from TRL1 to TRL3 or from TRL2 to TRL5 and so on. And with this information, you're able, or at least this company was able to fill in this matrix or the numbers.
So the thank you. I think the point of adding the time dimension or the level of effort to go from one level to the other, I think that's really very important. What I'm not sure I understand is how the numbers become non-subjective. Becoming ordinal. You mean because the sequence is that? Is that what you mean?
Well, with the time, so you develop your technology from TRL 1 to TRL 2, and then you have the time slot you needed, maybe 1 year or 5 years, I don't know. And from TRL 2 to TRL 3, it's again 3 years. And from this, what we did is an extrapolation from the past development into the future. So being at TRL 5 at the moment, for example, we can forecast how much time it will take us to get to TRL 9. And then we have, serious maturity. We can do this for all the technologies we are looking at. And so we can do an objective evaluation of different concepts or different technologies. So basically the forecast is scaling the whole thing.
So I guess you have to believe the extrapolation, that the extrapolation is accurate. Yeah.
Extrapolation is a point we have to look at in future work to improve this extrapolation. At the moment we stated we use an extrapolation like a simple Excel extrapolation or something like that, but you can improve this, of course. Yeah. But if you have a company existing for several decades, you can learn. That's what we learned. You can learn from the developments in the past, and you get kind of a feeling from how long will a certain technology take from TRL3 or 4 to TRL9, and then you can have you can combine this expert opinions with that extrapolations.
I think I'm always a proponent of trying to quantify things, but I always worry if we create numbers, and because they're numbers, we believe them too strongly.
You're right. Yeah, absolutely. But the time, I think the time is a pretty good scale, because you can measure it in days or months, whatever.
Right. Thank you.
You're welcome.
I'm sorry I keep asking questions, but I continue to invite everyone to put words in the chat. So I have a question also for Eike, if I may. There was a point that you showed that the design, you created a design using topology optimization and I think some mechanism analysis. But then you looked at the bio-inspired design and you mentioned that there was a 30% improvement, I'm presuming weight. So the question was, this improvement came from what? And let me just add the following. If I understood the concept, so you're essentially looking at design that you support the structure with some tensioning mechanism, right? And so this is kind of the old technology that you use in very successfully in the design of sailing ships, right? You have the stays, so you make very lightweight design. Actually, I always use this as an example of a very high technology in the 18th century. These were fantastic designs of, the tall ships. The difference was there that you adjusted the tension over time, how the weather changed. While in your design, you're basically doing continuous adjustment of the tension, if I understood it correctly. So I'm kind of curious, when you do that and you have this improvement, is it because of the control strategy, basically? If I understood it correctly, you have both a static design and so you do a combined design and control, because you have to have a good control strategy to implement it. Did I understand correctly?
Yeah, I'm very happy that you understood it totally correct, because I was not sure if a short amount of time I could explain it. well. To your first question, where's the 30% of weight reduction coming from? That's a very good question. Actually, the two systems that we presented were created. So what? No, let me start differently. The systems we compared were for very isolated boundary conditions. So we just did like one movement from A to B, and we said, okay, motion planning can be free. So we assume that most of the weight reduction results from the engines, from the joints to relocating them to the socket of the robots. But we also assume that we have some weight reduction by the control you just mentioned, and the ability to control the stress in the structure. So we actually need to investigate that more thoroughly, and that's why we wanted to look at torsion with a very basic example and excluding all the like the other factors like weight of the actuators and so on. And sorry, I forgot your second question, but I think it got to
all I wanted to mention again from experience of my own some years ago, we looked at combining optimal design with optimal control to have optimal system design, because traditionally the controls community and design community are completely separate, and the one takes the other as given. But in fact, if you can do this simultaneously, you can get better system designs. And usually that happens with the control function or the optimal control problem being nested inside the optimal design problem. So maybe that's something you can play with and see if that's useful. Yeah. So let's see, we have 3 minutes left. We didn't ask any questions from Patrick. So I have one question. Patrick, you're advocating, let's use aluminum foam. Let's get, basically, people don't know enough about it. Let's make sure they do. And I think Felix or someone mentioned the ASPE charts, which are now actually part of ANSYS, big conglomerate, right? Do you see this type of design of materials, let's say, like aluminum foam, being implemented in a tool like the Granta design tool that's based on the ASPE charts? Because they're very useful. I mean, so I was just wondering if you have thought about that.
Yeah, actually, at the moment I am looking for a selection method to use the material most effectively. So yeah, it's always important to know where the material has it or where the advantages are, and then you can use it with a clear target. So it's always important to know the motivation for the lightweight, and then you can use the aluminum foam also with Ashby's selection method, or you include it, and yeah, you can use it correct or better. I hope this goes. Yeah.
Maybe, yeah. I was just thinking that now that ANSYS is in charge of all this, they bought the company, that maybe you can talk to them, maybe start a project with them to see if they can support in the library of materials. Anyway, just a thought.
We are in contact.
Just a thought.
Yeah, thank you.
Yeah. Okay, Felix, would like to say a few words on your last comment, and then we can conclude the session.
Yeah, I was commenting on the re-comment of Professor Fadel, and he's absolutely right that the tools for actually applying lightweight design became better and better, and there are more opportunities than ever before to perform lightweight design, materials, sophisticated tools, and so on and so on. lightweight design is getting more and more attention in the daily design business of the companies, because the tools itself became better and the materials came better, hybrid materials, etc., etc. But for most of the companies, they are still very expensive. So in most companies, especially in the small companies we are dealing with as well, lightweight design from a material point of view is already changing from steel to aluminum, to normal, totally basic aluminum. When this is lightweight design, but the small companies are much more interested in it, I think the better tools and the better and more sophisticated materials are not the entire answer to that increase in demand.
Very good. Thank you. So I think we're out of time. So I would like to thank all the speakers and give you a hand. I wish you a nice ending of the conference today. So thank you again for the nice presentations and the conversation. And thank you, Robert, for making sure we didn't make any mistakes here. Goodbye.
Bye. Goodbye.
Thank you, Panos. Bye-bye.
For the chair. Bye.
Bye.